We're finished now with C, and we're moving on to C++, which also is a self-managed, typed, compiled native language, which means you have to do a lot of the work, in many cases, to be careful with memory. And we're going to talk about how if you can avoid doing that work, you always want to avoid doing that work, because that's where the majority of the bugs come from. You might consider C++ a mid-level language in that it has lower-level capabilities. It's natively compiled. It's still close to the hardware, but it has object-oriented abstractions just like higher-level languages, but you still have to manage the memory by and large. C++ was developed in 1979 at Bell Labs as an enhancement to C, and it was called originally C with classes and later called C++ in 1983. I think I've mentioned this before, but generally you prefer to use a high-level language if you can, C# or some interpreted language like Java or Python, because they're just safer. You don't have to do as much memory work. However, they don't work for every situation. High-performance networking applications, kernels, hypervisors, desktop applications, embedded software, entertainment, they're all still written to this day in C and C++. So yes, there's danger, yes, there's great responsibility, but there's also a massive community and a large amount of different tools, compilers, projects like LLVM and Clang to help you audit your code statically and do better with compiling and writing C++. Practically every computer language has gotchas, constructs or combinations of constructs that software developers are likely to use incorrectly. Sadly, the C and C++ languages have an unusually large number of gotchas, and many of those gotchas tend to lead directly to dangerous security vulnerabilities. That's a quote from David Wheeler, and I think it sums up pretty well the pros and cons of a language like C and C++. So because it's so closely related, yes, C++ has many of the same features as C, the same code organization and types, operations, arrays, escape sequences, pointers, basic logic like for loops and while loops and whatever else. Building is similar. Shared IDEs like the Visual Studio platform. You can still use functions, so a lot of similarities. However, of course, there are differences, and that's a big part of what we'll be talking about. The fact that C++ is object-oriented, and you can reuse those code and data objects to do various things, and we'll look at some of those. Different compilers, extended concepts and syntax, like classes, virtual functions, we'll dig into those. Extended standard libraries, for example, you would use the cout instead of printf. New types like vectors and lists and arrays, and you prefer to use those whenever possible. And one of the first tips I'll give you as far as do's and don'ts is don't mix old C stuff when writing C++, although it's perfectly valid to do that, and you'll see that a lot. And it's a good indication if you see code that's C++, but you see a lot of very C-like features in it, you know that whoever wrote it is maybe not super familiar with C++, and there's probably going to be some mixing and bugs because of that. As an example of some of the mismatched things you don't want to do, particularly as it relates to memory, again because memory is so important, if you declare a local variable, which you definitely want to as often as possible because there's less lifecycle management involved. You don't have to free or delete or allocate or whatever. If it's a local variable, it'll come and go in its own scope, and that's the best way to do memory. So don't ever try to delete it manually as in here. When you use the wrong memory allocation on the wrong type, bad things will happen. On a low level, you'll end up manipulating pointers and memories and things that get scary from a security point of view. Again here, a local array, and there's no need to delete it. Look here and we see that we tried to malloc some memory, and then we delete it, which is the wrong version of the allocator. If we malloc, we free. If we new, we delete. Same thing here, we're mixing the wrong allocators and deleters. So let's look at the correct way. If we create a new object, then we use delete. And if we create a new array, we use the delete array. Let me give you another example of a no-no, something I've seen in C++ that really shouldn't be there. It's the use of VLAs, which are variable length arrays. They're an alternative to container classes, and they look and feel a lot like C arrays and give you direct access to memory, where C++ container classes give you better protection. If you look at the VLA internals, you'll see here we're creating 10 new classes, which will use the default C++ allocator unless overridden. And you'll end up with heap memory. You see you have chunk header, so the allocator keeps track of the memory in some way, and you have a count of the size of that memory. And the user is returned a pointer to the first object in that memory space. And we can see very clearly that if there's a problem that happens, if we overwrite from, say there was some internal buffer A and you overwrite past B and into the next vtable pointer of the next object, you're going to have a real big problem. So when that next object is used, instead of running the code associated with the object correctly, bad things will happen. Back to talking about some of the new things in C++, we have namespaces, which gives you a way to group classes and indicates where all that code is located. And you have a namespace like standard, which is pretty typically used. Also, you don't have to return a value. Instead, classes can throw exceptions. Here's a typical C++ example of a try-catch block where you try to do some division, but if the operand is 0, we can't divide by 0, so we throw an exception and we catch that and we tell the user that there's bad operator involved. Here's another example of an exception, and this is a typical case where things go wrong. So in main, we create a new cat called Molly, and we tell Molly to eat her food, which runs some code, except there's an exception that happens in eat food. It throws up, which is just some exception which we can catch in the catch block. I know it's very clever. I hope you're laughing with me. I thought it was a funny example. The problem is we should have in the try deleted Molly, or there's some problem with object lifecycle management there. So we end up with a memory leak, or worse, maybe it gets freed twice and we try to use it after that, or there's all kinds of lifecycle management problems that can happen when it comes to creating and deleting objects. And so there's things like smart pointers, which we'll get to, that could help with that, and we'll talk about that later. The biggest new feature in C++ are classes, which allow for object-oriented programming, as well as other things like abstraction and encapsulation. And we're going to talk about that in a minute. So an object is an instance of a class. There's also templates in C++, which are generic argument functions or generic programming, and we simply don't have time to go over that too much here. I just want to say that templates are very useful, but if used too often or incorrectly, they can make the code very hard to read and audit. Okay, so what are some of these new features of classes? Encapsulation, for example, allows members to be declared as public, private, or protected, which allows you to kind of hide the internals of an object. We'll look at that. Inheritance allows one new object type or data type to acquire properties from a prior, like the circle becomes later a sphere or something like that. We'll see that. Polymorphism is the most useful and important, and it allows for a common interface for many implementations where objects act differently under different circumstances. Here's a simple example of encapsulation. We have a private member called total, and it's accessed through operators. You can get it, add to it, but only through a common public interface. So we see in the main program, adder A, and A you can add a num, 10, add a num 20, add 30, and finally you end up with some total like 60, but you're never directly accessing a private member variable. And that allows you to change the implementation under the hood without changing the interface you've exposed to the public world. Before I talk about the other OO features, I want to mention too that a common thing you might want to do is overload the assignment operator so that when you say my class equals this, then the code knows how to copy one object to another. Let's take a look. For example, if you had one date class equal another, what it would do is internally it would say day equals new date day, month equals new date month, year equals new date year. And it's a very simple concept. You're just programmatically defining how one object becomes equal to another of its type. So how does inheritance work? Well, you have a base class, which is the initial class, or also called a parent or super. Then you have the derived class, which is created from the base, and it also might be called a child or a subclass. And the derived class gets all of the data and functions of the base class, and it can add new or override existing member functions. Here's a very common example. You may have a shape where you can set the width or the height, and you have the protected internal variables there. We'll call that the base class. And then from that, you can create the rectangle. Just do class rectangle colon public shape to create a rectangle, and that gives you the derived class, and you add this getArea function. So to use the code, you instantiate a rectangle object based on the class code. You set its width and height, and you output the area, which is 35 in this case. All of that's well and good, and again, I don't have time to teach an entire semester course on C++, but just giving you a little background history and kind of refreshing your memory on how it works. Now, the polymorphism is a little more interesting. It allows you to provide new code with the same function name. Now, if the code in an object is static, the compiler knows what points to what at compile time, but typically the more interesting case is dynamic bindings, which means that a vtable has to be created so that at runtime, the program can dynamically figure out which member functions point to which code in an object. Also, there's an interesting thing called runtime type identification, which stores information about an object in memory if there's a need to look up type information. And the reason that's interesting, when we get to the reverse engineering course, we'll see that a reverse engineer can actually pull some of the RTT out of a binary to figure out some of the original class names, thereby helping them sort of steal or figure out the intellectual property that maybe the programmer thought they were hiding by compiling their code. I just mentioned dynamic bindings, and again, that works by creating a function pointer that's assigned at runtime. The indicator to the compiler that it needs to do this, to build these virtual tables, is you have to have this keyword virtual in front of the member function, and it has to be in the base class, not in the derived class. And of course, the goal here is that the functions have the same name, but different code, different actions. To better illustrate the point of dynamic bindings, let me give you a demonstration.